Data scarcity. It's the biggest challenge in applying machine learning to materials, science, and mechanical engineering. While computer vision and natural language processing have access to millions of labeled examples, experimental materials data tells a very different story. It's expensive, it's time-consuming, and most research groups work with datasets in the 500 to 1,000 sample range at best. This raises a critical question: which machine learning algorithms actually perform well when you're working with limited data? To find out, we systematically compared 6 feature-informed approaches on the same metamaterial design task using 800 samples, and the results challenge some assumptions. First up, random forest. This is an ensemble method that trains hundreds of decision trees in parallel and averages their predictions. Each tree learns from a random subset of your data and features, which reduces overfitting and creates robust predictions. Think of it like consulting 500 independent experts and combining their opinions, solid baseline performance, and a reliable benchmark for comparison. Next, XGBoost. Here, we see a fundamentally different philosophy. Instead of parallel training, XGBoost builds trees sequentially, where each new model specifically corrects the errors of the previous one. This gradient-based optimization has made XGBoost the go-to choice for structured data problems across industry and research. It earned second place in our ranking, excelling at capturing complex feature interactions while maintaining strong generalization. Then we tested LightGBM. This algorithm optimizes the gradient boosting framework for speed using histogram-based learning, binning continuous features to accelerate training dramatically. The interesting finding, our dataset wasn't large enough to show its full advantage. LightGBM really shines at 100,000 plus samples. With 800 samples, solid results, but not exceptional. Now, our top performer, classic gradient boosting, and honestly this surprised me, the foundational algorithm outperformed its more modern descendants on our metamaterial design task. The reason comes down to the bias variance trade-off. Traditional gradient boosting takes a more conservative approach, shallower trees, stronger regularization by default. For medium-sized datasets, this careful methodology made the decisive difference. Sometimes the steady, well-established approach wins over the cutting-edge alternatives. Our neural network ranked 5th. This result speaks to fundamental properties of deep learning rather than any implementation issue. Neural networks have enormous expressive capacity, but that capacity requires substantial data to learn meaningful patterns. With 800 samples, we simply couldn't provide enough examples for robust learning. It's a reminder that model selection should match your data characteristics, not just follow trends. Finally, support vector regression, last place in our ranking, but this actually aligns with its design philosophy. SVR was developed for very small datasets, typically under 100 samples, where kernel methods provide unique advantages. With 800 samples, we had moved well beyond its intended operating regime. So what's the takeaway? Algorithm performance depends heavily on dataset size, feature engineering, and problem structure. For our 800 sample metamaterial design task, gradient boosting proved optimal. Different data, different results. Curious to hear your experiences. What approaches have worked for similar sized datasets in your projects?